Hi, my name is Vinicius Mattoso, and I'm finishing my master in mechanical engineering at PUC-Rio. I'll present the work Reservoir Properties Estimation based on the pressure and temperature data using the ES-MDA. This work is a preview of my master test and was developed by me, Dr. Damarmaza, and Professors Abelardo and Márcio Carvalho. Here is the summary of this presentation, which starts with the contextualization of the work, followed by some explanations about the well-reservoir simulator used, the problem that we want to solve, the SMD method applied, and the results. The presentation starts with the contextualization of where our work fits in the oil and gas industry. This work belongs to the reservoir management area, which has much subdivisions, and our product is inside of the reservoir characterization. In a summary, a reservoir characterization means to estimate the reservoir properties such as the different permeability values and regions. To make possible the characterization, some data is necessary. And to obtain this data, the well test is commonly made. The well test consisting of obtaining pressure and temperature data from the wellbore after successively process of open and close the production valve, known as drawdown and build up respectively. Despite having both data available and with good resolutions, commonly only pressure data are used to make the reservoir characterization. A non-isothermal well reservoir simulator was used to build a set of simulated data. The LMMP group from PUC-Rio developed this numerical simulator using the finite difference method. It consists in a well-bore coupled with a 1D cylindrical reservoir for a single-phase fluid flow. Here is the set of equations solved by the simulator, which contains the reservoir mass and energy conservation, the well mass, energy and momentum conservation. So, the problem that we want to solve consists to estimate the permeability of the reservoir based on data. For this, a simulated data with non-permeability values are created and use an optimization method to make the history match, and then we achieve the permeability values from the reservoir based on this data. But in order to estimate a range of value and response and evaluate the parameter uncertainty, an ensemble of models was simulated and the history matching was made using an ensemble method to obtain a distribution for each parameter. The observed data was captured from the sand phase, that is the connection region between the wellbore and the reservoir. And to simulate the noise from the measurement equipment, a normal distribution was added into the simulated data. The method used to make the history matching variable uncertainty analysis was the ensembles multi with multiple data simulation. It is an ensemble method that made iteratively global updates with all the available data. Into the update formula, the matrix CMD and CDD are created in this way. Alpha is the inflection factor that obeys this formation rule. CD, which is one of the object of study of my master test, the covariance matrix of the observed data measurement error. Duke is the observed data that we want to fit, and D is the simulated data. And the reservoir analysis has a skin zone with a lower permeability near the well, followed by a homogeneous region until the end of the reservoir. In red are the values that we want to estimate. And analyzing the log-log derivative plot, we can observe that pressure has a single plateau, which indicates a single permeability level, and the temperature has two plateaus, which indicates two permeability levels. Here in blue is the observed data, which is not possible to observe those plateaus. And in order to evaluate the robustness of the ES-MDA and the benefit of the using combined data, harmonic noise was also introduced in the pressure data from the combined observed data to simulate the tidal effects. The magnitude of this harmonic noise used is bigger than the magnitude found in literature to make this evaluation. Here in blue is the magnitude found in the literature, and in orange is the magnitude used as reference for this work. With the introduction of this harmonic noise, the graphical analysis made through the SAM log and the log became more and more complicated, requiring a data filtering process which leads to loss of some points. And this work, no data filtering process was made into the observed data inserted into the ES-MDA method. The ES-MDA performed 4 simulations considering sample size of 100 and the inflection factor was set constant and equal to 4. The log scale was reused to reduce the permeability values and give this Gaussian format required for the method. To create the initial distribution, a normal with mean 5 and a standard deviation of 1 was used to create both log permeability distribution and also for the alpha skin, which correlate the well and skin radius. For the porosity was used a normal distribution with mean 0.2 and a standard deviation of 0.05. The CD matrix used comprised of two diagonal blocks associated with each independent observed data. The CD matrix configuration used was created based on a sweep KD thesis that used the Joule-Thomson coefficient to correlate the pressure and the temperature data into the Levenberg-Marquardt method. An additional weight of 10 power less 4 was also used into this configuration. And due to the magnitude of the pressure is much different than the temperature, the observed data were normalized by the respectively initial values. And starting with the results, to evaluate the use of the coupled data, we compare the estimation for each parameter considering only pressure data and using the combined data with different noise amplitudes. The red line is the expected value for each parameter. Here, we can observe that even increasing the harmonic noise, the combined data is still providing an accurate estimation for the skin permeability, better than the simple pressure analysis. And for the permeability out of the skin zone, as we increase the harmonic noise, the estimations decrease, but it's still better than only pressure data. For the porosity as well as the alpha skin, the temperature data are responsible for a good characterization, and as the harmonic noise only affects the pressure data, we did not observe large variation to the estimations, reinforcing the fact that using combined data improves the reservoir characterization even in case with a high level of noise. Here is the result of the simulated evolutions for the final ensemble of parameters. The evolution oriented when the initial distribution was inserted into the flow simulator is in gray, in red is the observed data that we want to fit, and in blue is the response when introduced the last ensemble into the flow simulator. This figure contains the analysis that considers only the pressure data, that the history match is closer, but the model of parameters are incorrect. And here is the data matching for the coupled data considering the highest amplitude in the tidal noise. In this configuration, the data matching and also the parameter estimation achieves accurate results. And as conclusions of this work, we have successfully implemented and applied the ES-MDA method. The coupled pressure and temperature data can be used to estimate the reservoir parameters. The addition of temperature improves the near well and porosity characterization, and the ES-MDA seems to be a good candidate to use the observed data even with the highest tidal noise effect without any filtering process to estimate the reservoir parameters. Finally, I'd like to say thank you for the attention and I'd like to say thank you for the financial support from those institutions.